In this video, we're going to finish up our proof of proposition 1.3.6. I said I was willing to leave part A as an exercise, and we proved part B in the last video, but I ran out of time and screen space and so on, so we're going to prove part C right now. So Bn converges to B. So we're going to start by letting epsilon be the absolute value of B over 2. And we're using the fact that Bn converges to B, and we're using the fact that we've proven proposition 1.3.3c. So by proposition 1.3.83c, there is an n, a natural number, such that if n is bigger than n, then absolute value of Bn minus B is less than epsilon, which is absolute value of B over 2. So, if n is bigger than n, then absolute value of Bn, triangle inequality Bn minus B plus B, the reverse triangle inequality, we want to use the fact that this is greater than or equal to the absolute value of B minus the absolute value of Bn minus B. You can write that is using the regular triangle inequality. Absolute value of B is less than or equal to the absolute value of Bn minus B plus the absolute value of Bn. So then what we write, so then this is greater than absolute value of B minus the absolute value of B over 2 is the absolute value of B over 2. So if n is bigger than n, then absolute value of Bn is bigger than the absolute value of B over 2, and that's a positive number by assumption B is not equal to 0. So Bn is not equal to 0, and that proves that this first part of our statement. Now, I could have taken epsilon to be the absolute value of B, and this part of the theorem would work, but I really did want, but the next part is going to work much better if we've got some wiggle room, if we've got a lower bound on the absolute value of B. So now, let's write that if n is bigger than n, then let's take this thing. 1 over Bn, I subtract off 1 over B, that's common denominator B minus Bn, whole thing over BBn. And so that's B minus Bn over modulus of B, absolute value of Bn. Modulus is another name for absolute value sometimes. B minus Bn. Since I've got this lower bound on the modulus of Bn, I can put a B squared in the bottom and a 2 on top, and I'm okay. So now we do our usual trick, pick epsilon greater than 0, and Actually, let's go back and name this first n we found. Let's call it n1 because we're going to have an n2 coming into play. Let n2 be a natural number, be such that if n is bigger than n2, then b minus bn is less than, let's say, epsilon times absolute value of b squared over 2. Because b is positive and epsilon is positive, our whole right hand side is a positive number, and so we can just use proposition 1.3 point into this thing exists and is a natural number, and we let big N be whichever is bigger, N1 or N2. And then if little n is bigger than big N, then trace through everything. 1 over b sub n minus 1 over b is less than epsilon. So we have that the sequence 1 over b sub n converges to the number 1 over b. And then to get an over bn converging to a over b, we use part A on the sequence an converging to a and 1 over bn converging to 1 over b. And that is all there is to that. In this video, we are going to talk about increasing sequences. So let me go ahead and define an increasing sequence. So we've got a sequence of real numbers. And this sequence is increasing if an is less than or equal to an plus 1 for all n, and it is strictly increasing if an is less than, not less than or equal to, strictly less than an plus 1 for all n. This is the definition that our book uses. Some books use increasing for what we're calling strictly increasing, and then they use non-decreasing to mean what we call increasing. That usage is a little bit more precise, but it's also a little bit more confusing because it's got the word decrease in it to talk about a sequence that's getting bigger, that's staying the same or getting bigger. It's got a non-decreasing opposite of decreasing. It's easy to miss the non. So this is our definition, and let's sketch an increasing sequence on the number line. Here is a 1, here is a 2, here is a 3, here is a 4, here is a 5. So if you look at it, you've sort of got two options. Either you're heading off towards plus infinity or you're building up against some finite limit. And there's actually a proposition for this. This is proposition 1.3.7. And this says that if n it is an increasing sequence, increasing or strictly increasing, so we just call those increasing. And if it's also bounded above, so it's not going off towards plus infinity. All right. So if it's not going off towards plus infinity, it converges. And not only does it converge, it converges to its supremum. All right, and let's go ahead and prove this. And we're going to prove this using our epsilon n definition of convergence. So let's pick, or rather, we start by directing the reader to pick an epsilon bigger than 0. And then our goal, what we want to show, is that there is a natural number such that if n is bigger than capital N, then an minus a is less than epsilon, or we can write this condition another way: a minus epsilon less than an less than a plus epsilon. So this last condition is what we're going to show. So we're trying to prove these two inequalities. So the right-hand inequality is pretty straightforward. Clearly, an is less than or equal to a is less than a plus epsilon for all n by definition of the supremum. A is the least upper bound, which means it's an upper bound, which means all the an's are less than a. So a minus epsilon is strictly less than a. So a minus epsilon is not an upper bound. On the set of all the an's, because a is the supremum, is the least upper bound, and it's less than the smallest upper bound. All right. If a minus n is not an upper bound, that means it's not bigger than all of them. That means there must be an an that's bigger than a minus epsilon. Let n be such that a minus epsilon is less than an. Then if n is bigger than or equal to n, then a minus epsilon is less than an, and it's a pretty straightforward word induction argument. And so I'm not going to go through the details to show that it's not just the next one that's bigger, it's all the ones that are after that are bigger too. So if we just disregard this thing in red, just look at the white bit of this chain. Just look at the white bits of this chain of inequalities. Then we see that. We have satisfied the epsilon n characterization of convergence. So we have that AN is converging to A. All right. I think we've got time for one more topic in this video. This is definition 1.3.8. And here we're going to talk about subsequences. So let's suppose we've got a strictly increasing sequence of natural numbers. And then if AN is a sequence, we're going to call this thing A sub n sub k from k equals 1 to infinity is a subsequence. And let's have a couple of examples. Let's let AN be 2 to the minus n. So our sequence of ANs, that's the sequence 1/2, 1/4, 1/8, 1/16. And then this thing is a subsequence. 1/4, 1/16, 1/64, 1/256 is a subsequence. And we don't have to put, so this one I of course got by grabbing every other term in the 2 to the minus n sequence, but you can skip around a bit if you want. Let's let AN be just the integers 1, 2, 3, 4, 5, 6, 7. Then this thing is a subsequence. 2, 3, 5, 7, 11, 13, 17, 19. I can just grab all of the prime numbers in order, and that gives me a subsequence. So a couple of things I want to emphasize. This is not a subsequence. So this is grabbing the second element, then the first element, then the fourth element, then the third element, then the sixth element, than the fifth element. This is not a subsequence because we are out of order. And another thing that is not a subsequence is we just grab the first element and repeat it. That is also not a subsequence. And here, and I'll close this video by stating a proposition. This is proposition 1.3.10. We will not prove it because the proof is an exercise. If a sequence AN converges to A, then any subsequence also converges to A. And this is why this is one reason I was so adamant that you can't repeat yourself. If we go back to our very first example, this sequence is of course converging to 0. This subsequence here is also converging to 0, but if I just grab the first element, if I just grabbed a half and repeated myself forever, then we wouldn't necessarily be converging to 0. The problems with this, with this anti-example are less obvious, but we do still want to insist that subsequences do have to be in order for various technical reasons. In this video, we are going to state an important theorem in analysis. You can tell it's important because it is actually named after someone. It's named after the mathematicians Bolzano and Weierstrass, who are the first guys to prove the thing. And it says, let's let AN be a sequence of real numbers that is bounded. Now, bounded sequences don't have to converge. There's the sequence 1, minus 1, 1, minus 1, 1, minus 1. That's bounded, but it doesn't converge. But it does have subsequences that converge. There's the 1, 1, 1, 1, 1 subsequence and the minus 1, minus 1, minus 1, minus 1 subsequence. Those do indeed converge. So, and that's not a coincidence. The Bolzano-Weierstrass theorem says that always has to happen. Then there is at least one, could be more, subsequence. That converges. And here is how we are going to go about proving this. So this is going to be a complicated argument, so let's draw a picture of what's going on. Here are numbers A1, A2, A3. I'm not going to bother labeling these, all of them. Let's say there's AK. And then what we're going to do is we're going to let, this is bounded, so it's got a lower bound x1, and an upper bound z1. So we let x1 and z1 satisfy. x1 less than or equal to an less than or equal to z1 for all n. And we're going to start, we have to start somewhere. We're going to let n1 equal 1. So our first point in our subsequence is just our first point in our regular sequence. And and just for the sake of simplicity, we're going to use it later. Let's let R be z1 minus x1. So x1 is less than or equal to an1 less than or equal to x1 plus r. So r is this distance, x1 is at one end, and a1 is just somewhere in here. Let's say this one is a1. Then what we're going to do is we're going to split the difference. We're going to let y1 be the midpoint, be halfway between x1 and y1 and z1. We're going to let y1 be x1 plus z1 over 2, also known as x1 plus r over 2, z1 minus r over 2, however you want to describe a bit. So now we have split this range, this x1 to z1 range, we've split it in half. So there's a bunch of points on one side and a bunch of points on the other side. Now, remember that our sequence is infinite. So that means we've got infinitely many of these an points, and we put them in two boxes. They can't both be finite. So let's consider this set. This is the set of all natural numbers such that an is in, let's make it the closed interval from x1 to y1. So if there are only finitely many of our points to the left of y1, we're going to let x2 be y1 and z2 be z1. And otherwise, we're going to let x2 be x1 and z2 be y1. And in either case, we've got that z2 minus x2 is r over 2, and the set of all natural numbers, let's say n has to be greater than n1, n is in x2, z2. That is infinite. You're allowed constant sequences. You're allowed the sequence that's just 2, 2, 2, 2, 2 forever, or that what we're talking is how many times your 2 shows up. So that's why I'm counting the number of n's, not the number of an's. So let's go ahead and draw this picture again. We've got our x2 here. We've got our z2 here, and we've got infinitely many points in here somewhere. And now there might be some points that are on the outside, on one side or the other, or that might even include our point AN1, but that's not going to matter too much. And we're going to let N2 be the minimum. In the natural numbers, you can always take a minimum of that set I just wrote down. And this is why I put in this and this is why we put in this n bigger than n1 condition, because we want n2 is strictly bigger than n1, because we're going for a strictly increasing sequence, because that's how subsequences are supposed to behave. And two things I want to point out before we move on is that x2 is bigger than or equal to x1, and x1 is x2 is less than or equal to an2 is less than or equal to 2 to the 1/2 r, but I'm going to write that as 1 minus 2 because we've got lots of 2's showing up here, and it's going to show up in a pattern. So how we're going to finish this proof is we're going to repeat this process. So let's write down some precise instructions for what to do once you've figured out the jth term. How do we find the j plus 1th term? So suppose we have found xj, zj, nj, and a sub nj with the following things are true. We've got xj less than or equal to anj less than or equal to zj. zj minus xj is 2 to the 1 minus j times r. That's why I wanted it to be 1 minus 2 before. And the set of all natural numbers such that an is in the interval from xj to zj, and we might as well insist that n is bigger than nj minus 1. Throwing out finitely many numbers won't hurt is infinite. And then so let's suppose we've done this. We just did this we just worked this all out for j equals 2, so now this is a basic induction argument. What do we do next? We let yj plus 1 be the average of xj and zj, and then if you've only got finitely many points on the left, if you've only got finitely many points on the left here, you grab the right half. Otherwise, if you've got infinitely many points, you grab the left half. And then, in either case, this first condition is true for j plus 1, or at least it is if we're going to let nj plus 1 be the smallest natural number that puts our an in the right place. And by assumption, this set we've just written down is infinite. So this condition is also true with j replaced by j plus 1. So this is giving us 3 sequences. We've got our xj's, our zj's, and our subsequent anj, j equals 1 to infinity. And let's see, one more fact that I didn't write it down, but which is true and which we're going to need to use. The sequence of xj's is a non-decreasing sequence, and it's pretty clear from this condition that that's going to be true. So the sequence of xj's is increasing, not strictly increasing, you probably, but definitely increasing. So it has a limit x, and also anj minus xj that is converging to 0. And so by proposition 1.3.6a, ANJ, that's XJ plus ANJ minus XJ, that is converging to the same limit. So that is how we get a convergent subsequence, this sequence of the ANJs. It's obviously a subsequence, and it converges to the same limit as our XJ.